To continue what I was speaking about yesterday, maybe there is one point I didn't stress enough. That is, what kind of questions in coding theory are well treated by algebraic geometry and number theory. So, as I hope you remember, a code has several parameters, n, k, d, and q, which is fixed once and forever in a sense. Now, how to describe the space of codes? Which codes are possible, which are not possible? Of course, you can give very specific results. That is, you can say that we do know that k plus d is at most n plus 1. Then you produce a code. You say, we do know that a code with such and such parameters exists. But to make the question more regular, you need either to work with small n's. For small n's, you can at least hope to describe which codes actually exist. Or you work with large n's. For large n's, what you usually do is you introduce two other parameters, r, which is called the rate of code, the transmission rate, because of, well, you may as well forget that codes are applied, but they need it, which is k over n. This is a parameter that describes the redundancy, and delta, which is d over n, which is, roughly speaking, 2 times the number of, 2 times the probability of an error with which you still can work in a sense. I won't be more precise on the point. Here, one thing I can tell you why 2 times, because if you consider a code as a metric, as a set in the metric space, so this is fq to the n, and here is some code here. And there are some points, and you want that the distance from one to the other is not too small. Then what you do is you draw circles or balls that do not intersect, so whose radius is slightly less than the half the minimum distance. Then they do not intersect, and then you hope that if the receiver gets a point, instead of this point gets this point, then you can somehow recover the original one from the one received. So that's on the information theory side. So here you draw a standard picture where you have delta here and r here, and you see immediately that any code corresponds to a point in a cube, in a square, sorry, 1 by 1. Then for each code you put a point. So there are a few points here. This is 1, 1, 1 code. Then there are some points here, and there are many points that are bad. Now you take the limit points of this set. This is a discrete set. Not a discrete, but this is a set. So you take the limit points of this set. And then Manin proved the following theorem, which somehow made the situation correctly understandable.
You let k and n and d and run, just so for all n.
Yes. Yes. So this point corresponds to 1, 1, 1.
Yes, you don't fix n.
Yes, and then I don't fix n, and I draw r and delta for any code. Of course, some points come in with multiplicities and things like that. And then what happens is that if you have a point here, there are certain constructions that make the code worse. which is that out of this point you can get a point which is slightly under, slightly closer to the origin, so to say. And if you take all this information in, you can prove that the limit set is under a curve. So there is some curve, we do not know which one, that starts here and ends at the point q minus 1 over q, and which is continuous, maybe differentiable at the ends, and nothing is known in between, and monotonously decreasing. And then it goes along the axis. And the area below this curve, this unknown curve, in this area, each point is a limit point for those points corresponding to codes. And over it, no point is a limit point. Some discrete points can be over there, but they accumulate on this curve if they may come closer, but there are no limit points above. So in a sense, the principal problem of parameters of codes is to describe this curve. No ideas at all. What is known and what can be done is that either you produce an upper bound. This condition here gives you that this curve is definitely under the diagonal line. In fact, it is also under the line joining these 2 points. And there are some other bounds that are over this unknown curve. We call them the upper bounds. On the other hand, you can prove that some codes do exist. This gives the lower bounds. So there are some lower bounds here. And in fact, one of these bounds is very famous. It's called the Gilbert-Varshamov bound. Gilbert-Varshamov bound. And it is known that a linear code, as parameters of a linear code with probability 1 in some certain but strict sense lie on this bound. So an average code is somewhere here. And algebraic geometry codes, as I have told you, they have the parameters k plus d are at least n plus 1 minus the genus of the curve. And when you divide by n, so let me divide by n, here I get r plus delta, here I get 1. I ignore the constant, and here I get minus g over n, and here I write r plus delta, and so it's asymptotically somewhere here. So what I have written here has no sense at all, because I do not know what is g over n. G changes. When n grows, you have to grow the genus. But what is very important for me, that the behavior of, and the quality, in a sense, of the codes you obtain depends on the ratio between the genus and the number of points on the curve. And if you draw this bound here, using modular curves, you prove that if Q is large enough and if it is a square, then these curves lie on such a curve that it does intersect this Gilbert-Varshamov bound, that is, ameliorates on it in a certain region. So you need not keep in mind this picture, but what you need to keep in mind is the fact that it's the genus to the number of points. So I'll write it here. That is important. Number of.
I mean, n is n is somehow related to.
Absolutely, absolutely. So, so we already for this ratio here, or better to say to the inverse ratio, let this be g over n and the number of points on the curve. Then for n over g, which is easier for me to write, we do know that it is at most square root of q minus 1. This is Drinfeld-Ladutz. And there is some other information on this quantity, and many people study this ratio. Let me, so the best result obtained here is, it's not the best one nowadays. There is an amelioration, but a very small one by Xing. This is what we obtain. Sorry, that's nonsense. Yes, right, that's true. Good. Now I erased this picture. Yes, and in this picture I should say that people from coding theory see that a family of codes, a sequence of codes with growing n, is asymptotically good if it doesn't lie on the bounds. So anything here would be asymptotically good. And asymptotically good is very difficult to construct. If you are interested in direct constructions, each time you just fabricate something by natural means, each time you get on the boundary. So
asymptotically good means what?
Asymptotically good means that neither r nor delta is zero at the limit.
By definition.
By definition, yes. So now I erased this, and I'll finish what I was speaking about yesterday. That is how to use number fields to construct good codes, because about function fields I have already told you. So for a number field, you have a number field k. You take the ring of integers. You take a fractional ideal, or you just take an ideal, say A. This corresponds to the divisor we had yesterday. Now you take the space of, the analog of the space of functions associated to this ideal, which is just A minus 1. And this will be the source of elements. Then you map it, so you embed it into K. This K, you embed it into the product or a certain number of valuations. You fix a finite number of valuation. You put it into, embed it into local fields, and here you are lost. Because these fields are of different, if you just take, reduce, say, these fields by the maximal ideal, what you get is of different characteristics, and some of these places are Archimedean, and so you are more or less lost. So the clever method of Lenstra, which I consider to be extremely clever, but also extremely ugly. I do not like this construction, but is that what he does he fixes a certain range. So he says that let the norm of V be between Q and R, for some Q and R. And then what we do with the with finite places. So for a finite place here, we just take the reduction modulo, the maximal ideal, and you get into F, say F or R, Q, S, Fs. And you choose the places in such a way that S is in between of R and Q. And then this is a kind of an alphabet. Then you embed, not as a field, but as a set, Fs into Fq. And you see that while we just do not use all the elements of the alphabet, but some of them.
So Q is fixed for the,
Q is fixed.
for the whole story.
Q is fixed and R is fixed for the whole story. And so here, you get this and you embed it into Fq. So this for a finite place. What do you do for an infinite place? For an infinite place, you take not all the elements here, but only those that fit into a certain cube. So in R, well, you may consider that the field is totally real. It's easier, but it doesn't change a lot. So R to some power m. In this R to some power m, you take a cube. And then what you do is that along each axis, you cut this cube into q parts equally. And the same in the other direction. And you see that if a place, if a point of this set gets into this square, then you see that the corresponding element of the alphabet is 2, 2. So you see that it's extremely artificial. And of course, what you get would never be a linear code. It would be just a subset. Yes?
How do you project from a local field to the residue field?
Well, I factorize, but first of all, yes, I take, I would say that the easy thing to do would be that I want a minus 1 lying in the integers. But you can do the same for fractional ideas as well.
So you don't project from the field itself, but from...
Yes, because this always lies in a certain ring.
Maybe the source of the arrow is a bit confusing.
Yes,
Of the arrow modem V, the source goes to confusing.
Which one? This is. Yes, yes.
Definitely not the whole KV, but
Yes.
but maybe change
Of course. Then, yes, let me write OK here and OV here. Then it will be clearer. Yeah. But that's a technicality you overcome easily. So doing all that artificial thing, what you get all of a sudden, and then you use, you have to choose fields. And to choose fields in the number field case, the only thing you are able to do, there are no modular curves. So, and unfortunately, I do not understand what is a proper analog of a modular curve or in the number field, for a number field. So when I say a modular curve, I mean already a reduction to the finite field.
But modular curves, can you remind me, they rose as some champions with respect to some quantities?
Yes. Modular curves reach this boundary. So for a modular curve, you have, if you choose a proper, well, you should suppose that Q is a square, and that your modular curve is of a certain type, which means that usually you define this curve over a field which is f square root of Q. And then you use the fact that all points on this modular curve that correspond to supersingular elliptic curves are defined over Fq. Not over the ground field, but over Fq. And there are rather numerous. And that's why the modular curve has lots of points over a finite field. So that's for yes, and the modular curves have n over g, roughly speaking, square root of q minus 1. I mean that the limit gives you this. So you construct this ugly nonlinear code, and it happens that its parameters are almost as good as you can get in this case. Of course, not exactly. So if instead, we have new modular curves, and then the question is, where do we get good sequences of number fields? I'll speak about this a lot, both today and tomorrow, but the main source are Golod-Shafarevich towers and ramified tower class field towers, and with certain conditions.
Sorry, can you ask me?
Yeah.
Your data should consist of a number field and a fractional ideal.
Absolutely.
So you just don't. You don't precise the fractional ideal when you say that.
Yes, of course, you can. You should have to choose the fractional ideal, but it's not the principal point. Just as for algebraic geometry codes, to choose a divisor is not very important, except in some special questions. So you just take a divisor whose degree satisfies certain conditions that you need. It's the curve which is difficult, not the divisor. So the same thing here.
Construction at the infinite places, you take a point in OV and you reduce, so to say, with respect to this lattice.
Yes, that's it.
Modulo Q.
Modulo Q. And so what you get at the end, you get something. So after all this, so this is for finite places. So this grid is for infinite places, and what you get, it lies in fq to the power n, where n is the number of places. And the subset is a code, and then you estimate its parameters. And its parameters happen to be and these codes happen to be asymptotically good in the following sense that let me take the limit. Yes, so r plus delta r plus delta times log r q, I think, or maybe vice versa. Let me have a look. Yeah, so here it's written in the following way, that R is asymptotically at least 1 minus delta, just right here. But this 1 minus delta is multiplied by log base QR minus gamma, where gamma is the limit of G over N of this quantity, which is worse than this thing because of two reasons. First of all, here 1 minus delta is multiplied just by 1, and this is smaller. And next, here this gamma is very good. And here we do not know what it is. But anyway, they are asymptotically good. So that's an old result of Lenstra. Now, what I plan to do next is to instead of this ugly construction, do a very powerful one. I'll give you a beautiful construction, but I won't get a code. So here we stop, and I turn to this picture. So what is a code by definition? By definition, a code is a sphere packing in this space. This is a space having measure and matrix. So if you have whichever set you like, if it has measure and metric, you can define a ball, you can define a volume of that ball, and you can define the following quantity, which may exist, but not always, which is that, so suppose you, instead of fq to the n, you just have something, say v, a metric space with a measure. Then you have a subset here, which may be finite or infinite depending on v. Then you measure the minimum distance. So you take, this subset should be discrete in the sense that the minimum distance, the infimum should be positive, strictly positive. Then you take half of this minimum distance. If the space is discrete, anyway, you take open balls here, then these open balls do not intersect. And then you define the density. So the density of this particular, this set of centers, I call it a sphere packing. And the density of this sphere packing, let me call it P, is defined as the ratio of the volume inside the balls to the total volume of the space. Now, of course, the total volume of the space may be infinite. So if you take a Euclidean space, it's infinite. Then what you do is you take a large box, you turn this box to infinity, and you take the ratio inside the box, and then you pass to the limit. The limit may exist and may not exist. Yes?
So a sphere packing is a pair of a subset of metric space and a real positive number?
No. A sphere packing is you fix a space with metric and measure. So V is fixed. After that, any subset here is a sphere packing. It is non-degenerate if the infimum of distance between 2 points in this subset is strictly positive. Then it may have a density. If it does have a density if the volume of the total space is finite, and it may have a density if it is infinite.
All balls in this packing have the same radius?
Yes, all balls in this packing have the same radius. This is a parameter of this packing. So packing is just a subset. I would say that the packing is non-degenerate if its density is neither 0 nor infinity. If it has a finite density, then I'll say that it is infinity. It can't be, sorry. If this density exists and is non-zero, I say that this is a non-degenerate sphere packing.
So the measure structure on your metric space must be compatible with the metric?
Absolutely. They must be compatible. Now, the case that will interest me, which cases are natural to consider? There are good spaces. So a good space is usually a space that has a large group of automorphisms which acts at least doubly transitively on it, or something like that. And because of that, people like this Hamming space FQ to the n, projective space over a finite field you can consider, Euclidean space, a sphere in a Euclidean space. So you get spherical codes or spherical packings, whichever you prefer to call them, and many others. But I'll now concentrate on the case when this is just R to the n. So this is the classical sphere packing problem, how to pack equal spheres in a Euclidean space so that the density is good enough. So either you ask what maximal density can be achieved and which structures attain that maximal density, or you at least ask, especially in asymptotic problems that we'll get as analogues of these, you may ask of good sphere packing, saying that a series of packings with growing n here is asymptotically good if a certain limit, I'll write it out in a while, is non-zero. So now, since you are not the students of the first year, I'll totally ignore the existence of the limit. You'll look into it yourselves. The general idea is that when I speak about the limit and the limit doesn't exist, that just means that you should take either the lower limit or the upper limit, or you should take out of this family where the limit doesn't exist, you should take a subfamily where the limit exists, or something like that. So that's in this particular theory, that's not very important. You can always treat the difficulty that comes out. But of course, if you want to provide a sphere packing that has no limit at all, you do it easily. A counterexample is easily constructed. So we have R to the n, and we have two parameters, and these parameters are the packing is inside here, and it has two parameters. One is the minimum distance, and another one is the co-volume. And another one is the density. And now what you see is that in a Euclidean space, you can multiply everything by a scalar. So scaling, the balls become larger, the minimum distance becomes larger, but the density doesn't change. Therefore, this is the only parameter here which is important. Now this is an analog, this sphere packing is an analog of a code. And what is an analog of a linear code? So an analog of a linear code is a lattice. So instead of considering just any packing here, I'll consider an additive subgroup in Rn, which I'll call a lattice, which I presume to be discrete and of full rank. Why do I need discrete? Because I want the distance to be non-zero. And why do I need the full rank? Because I want the density to be non-zero. If it's not full rank, it's definitely zero. And then it has two parameters, the length of the minimal vector that I call D, and the covolume, which is the volume of, so if this is a lattice, you take the fundamental domain, and the volume of this fundamental domain is the covolume of the lattice. This is something regular. So this is your lattice, and so on. Now, what you can do, you take the fundamental domain here, let me draw it larger. So let this be the fundamental domain. Then you have some balls inside. So you have a ball here, and 2 to the n balls at the total. These two should touch. And what you see is that if I cut this ball in 4, you see immediately that the parts that go inside the fundamental domain, if you replace them, if you shift them, they form just one ball. So you have one ball per fundamental domain. That is that you write out the density easily if you know the co-volume and the distance. And the formula for me not to be mistaken is well, of course, one ball per fundamental domain, which means that the density equals d to the n over 2 to the n, because this is half. And then you should multiply it by the volume of a unit sphere, and you should divide all this by the co-volume, and the co-volume, I call it the determinant of the lattice. So. Then, instead of r and delta, what you do is that the analogues of this r and delta are is just one parameter here. So you should divide by something. You should divide by n. But to divide by n properly, you shouldn't divide the density, but its logarithm. So I say that lambda is minus the binary logarithm of delta divided by the dimension of the space. And so this is the parameter I'm interested in when I consider asymptotics. What's the reason to do this? That in a Euclidean space, there is a theorem which is an analog of what I told you here, that there is a certain bound, the Gilbert-Varshamov bound, with the property that with probability 1, any linear code lies on it. The same is true here. With probability 1, the density of a lattice packing is 2 to the power minus n, asymptotically. So this happens with probability 1. In particular, there do exist lattices that behave like this. Asymptotically, nobody, which means that lambda, the best, lambda that corresponds to this bound is just 1. So if lambda is less than infinity, I say that the packing is the family of packings in growing Euclidean spaces is asymptotically good. So asymptotically good means that you get some finite lambda at least. And then, of course, you want this lambda to be as small as possible, which will give you, because the density, so let me write it. Here, the density is 2 to the power minus lambda n. So that's how you put the question at the, in the asymptotics. Now, you may forget completely about, yes, now what good, where to get good sphere packings from. So again, the question is cut into, when have I started? Do you remember? Yes, okay, so I have lots of time. Of course, what is a natural way to put the question? The first question is, let n be 1. What is the densest possible packing? Well, here I do know the answer. You take integers on the real line, and the density, if you take the balls, these are the balls, they touch one another, and the density is 1. So, what happens in dimension 2? In dimension 2, you have the following thing. You take the string of circles, and then you take another copy of this string, and you fit it from above. Yes, and now let me ask you a question. Do you already see the number theory here? I do. Because if this is 1, this is square root of minus 3 minus 1 over 2. Square root of 3, sorry. Minus 1, no, of minus 3 over 2. And plus 1. Yes. This is the ring of integers in, this is OK for k equals q square root of minus 3. But also, you are not so narrow-minded as to see only the number theory here. You also realize immediately that this is that both this and this are the root lattices for system of roots A1 and A2. So you continue this, and up to n equals 8, you get root lattices. So A3, A4, then you get D5, A3, then you get D4 and D5, and then you get E6, E7, and E8. And these are known to be the densest lattice sphere packings.
Do we have number field interpretation of this?
No, not always. Or better to say, always, but not directly.
Not like that. Lattice is okay.
Not like in dimension 2. Not like in dimension 2. By the way, up to n equals 4, as far as I understand, we know that this is the densest packing, not only among lattice packings, but among any packings. But, sorry? 3. And what Musin proved about 4? It was the Kissing number. It was the Kissing number, sorry. For 1, 2, and 3, we know that they are the densest possible. They are also pretty dense near to the upper bound for n equals 8, and for n equals 24, the least lattice that is the densest known is pretty close to the best possible, but as yet it's not too much that we know. Now, when we do not know the answer on a finite level, what we naturally do, we tend n to infinity. Now I'm interested in lambda in the asymptotic behavior when n tends to infinity. That is, I'm speaking about a lattice, but I always mean that it is one in a sequence of lattices with growing n, and that I consider it asymptotic. I want to consider its asymptotic behavior. Let me first write out the formula for this lambda in terms of D and in terms of D and covolume. And the formula will be that lambda of a sequence of lattices with growing n is asymptotically a constant which is minus log square root of p e over 2. The log, as far as I remember, is binary. Plus log square root of n minus log d of L, d of the same thing. And plus, well, maybe I'll write just d of L, and then I'll explain you what inaccuracies down here. And plus 1 over n log of the determinant of this lattice. What I mean is that you take just one lattice in a family, you take its distance, and you take the determinant. And of course, the distance and the determinant can be changed by scaling. But this, if you scale, this d is multiplied by something, and the nth root, small n and capital N, are the same thing. Sorry. But this quantity changes, but by exactly the same constant.
But that is, can't you somehow compare the distance with a determinant from Minkowski or something like that?
Well, the distance and the determinant, you see, neither for a lattice, if you consider it up to an action of scaling, has neither distance nor determinant. It has only the relative thing. And so the relative thing is this sum minus this logarithm. That is that in your family, in all constructions that I'm going to consider, quite naturally, this d will be of the order of magnitude log square root of n, sorry.
But isn't that, so to say, the shortest vector somehow, the distance?
It is. But
Euclidean metric. So you have a lattice. You have a lattice with metric.
Right.
And so you get the first successive minimum of the.
Yes, absolutely.
Which is related to the determinant of the lattice.
All right.
So
All right.
it would somehow express. So it is a distance.
It is related, but it is not determined by.
Equal. No.
And so I'll give you just one construction to start with, and you see how it works. So the construction is that I take a number field k, and just as I did before, I embed this k into the product of kv, and this time all my places will be Archimedean. I just take all Archimedean places. So this is r to some power s plus, times c to the power t. This is the number of real embeddings. This is the number of complex of pairs of complex embeddings. Now, of course, since the number is finite here, k is not discrete there. So instead of k, I take the ring of integers. I could as well take an ideal here. And the ring of integers is already discrete here. And now I should say that this equals, or better to say is isomorphic to r to the power n, where n is s plus 2 times t. And while doing this, I'll make a small trick, which is that, well, if I take an element here, which is A, then what it is mapped to. So I'll map it to AV1 and so on, AVS. And then I have complex values. So it will be BVS plus 1 plus ICVS plus 1, and so on. So this is an element here. And to get an element in Rn, I'll map it into, again, AV1. I'll just write A1. A1 AS. And then I won't take B and C, but I'll take square root of 2 times B S plus 1 square root of, and then square root of 2 times C S plus 1, and so on. So I scale the complex part by square root of 2. Well, if you do remember the formula for the discriminant, you easily see that I need that to get the discriminant of a field, the discriminant of K usually is written out as 2 to the minus t times the determinant of this lattice. And because of this scaling, I get rid of this 2 to the minus t. So the determinant of the lattice will be exactly the covolume will be exactly the discriminant of K by definition of the discriminant. So this I know how to determine. Now I need the minimum distance. For the minimum distance, the argument is easy enough. Let me pass here. The minimum distance. Well, let the image of A, let me write it out just as now as A1 up to AN. So A is mapped to as A1, AN. And I'm interested in its length, which is the square root of the sum of AI's squared.
So you replace OK by L in a certain way?
Yes. So the image L is the image of OK.
In this
Rn. In this Rn. Yes. So the lattice is the image of the ring of integers. Oh well, no, it's too bad. I'll have. Well, I'll start with this, and then you'll just. Well, so what I'll do to make it easier to explain, but it doesn't change the matter at all. I suppose for a moment that my field is totally real. It just simplifies the notation. But you do not need it. So you see an argument immediately. So this is at least. So this AI's yes, so now you should use the algebraic mean, arithmetic mean inequality. Let me see not to be mistaken. Yes, and what you get is that 1 over square root of 2 square root of the sum what do I need? No. So arithmetic mean, geometric mean will give you square root of s over 2 here. S equals n, so I suppose that n equals s for a while, because here it's written in full generality, but we do not need it. The product up to n of ai squared. And you should take the root of degree 1 over 2n. This is just square root of s over 2, because this is the norm. And the minimum of the norm of an integer is an integer. So the absolute value of the norm cannot be smaller than 1. So you estimate it as square root of n over 2. It's because of the square root of 2 here, you get exactly the same answer for the mixed case as well, if you do not presume that it is totally real. Moreover, the shortest vector is the image of 1 and all the roots of unity. So they give you the shortest vectors. When you put it in here, you see that the order of magnitude, that this d is roughly speaking square root of n, and because of that, what you're actually interested in is the nth root of the discriminant. And so you have to produce sequences of fields where nth root of discriminant remains more or less constant. And how to do that? You take unramified extensions. But you need infinite towers of unramified extensions. And the only source of these infinite towers of unramified extension we know are the class field towers. So you construct class field towers, then you choose the best parameters, and you get something like lambda equals 2.2 or something like that, which is worse than the Minkowski bound. But the construction is direct and beautiful. You get a lattice, which is very natural to consider if you consider a tower of number fields. You see that all the parameters of a lattice correspond to extremely natural parameters of the number field. This is the discriminant. This is just the dimension. So everything is easy enough. And then, of course, you may try to play taking not the ring of integers, but an ideal in it. Of course, if the ideal is principal, you get the same thing up to scaling. So you need it to be non-principal, and you do not get much better. Where you get better are other constructions. So now I'll just announce what I'm going to start with next time, tomorrow, is that as soon as you see this additive lattice, you start to think about the multiplicative lattice. You take the multiplicative group of OK, which are the units, and you map it logarithmically like Dirichlet and Dedekind did for other purposes. And so I'll show you tomorrow that what you get is also asymptotically good and pretty interesting. So that's it.
So in principle, this is the same. It's the same type of construction as Lenstra, but more conceptual.
Well, Lenstra wanted to get a code. Because of that, he had to do those clever but ugly things I explained. And I just took the natural construction, and I saw what you get at the end. What you get at the end is a sphere packing. And in fact, many people also produced good sphere packing starting with codes and vice versa. It's another story, not that interesting for people who are mostly in algebraic geometry and number theory, but also very clever. And best possible results, in a sense, are obtained in the following way: that you take algebraic geometry codes, then you construct lattices from them, and again, what you get is complicated, rather ugly, but you get some records on that way. What I'm planning to explain today and what I'm going to explain tomorrow is rather what natural lattices you get out of number fields and also out of function fields.
So, and in the multiplicative group, you replace the discriminant by the regulator.
Absolutely.
But what then? I mean, what replaces the class field tower?
The class field tower remains the class field tower. Unfortunately, our knowledge of number fields is too poor to have a possibility to replace it by anything.